Okay, this next example is number 9 in your book, and again we have the same directions. So we're given another differential equation, and I went ahead and just I wrote my y, right? This is my power series solution that I'm assuming, and then I'm going to take the derivative, of course, because our degree here, the order of this equation is 1. Obviously, if you have a 2 there, then you take the second derivative, which I'll probably do in the next example. Okay, so let's go ahead and just substitute these values back into the equation. So we have x minus 1 times y prime. Well, it's just this guy right here. So my sigma starting from 1 to infinity, ncn x to the n minus 1. And then I'm adding 2 times y, so that's 2, and then this guy is my y. So Cn x to the n, and that's all equal to 0. And, right, so again, here's my, right, this was my y, and there's my y right there, and there's my y prime, and there's my y prime. So we have this factor of x minus 1, so we can go ahead and just distribute x, and then we can also distribute a negative 1, which is just going to change the sign. So we have the following summand. Ncn x to the n minus 1 times my x that I'm distributing. And then minus 1, well, it's just going to be minus sigma starts from 1 to infinity, and Cn x to the n minus 1. And then I'm going to move over because I write really big. 2, and then we have our last summand, Cn x to the n equals 0. Okay, so let me make this a little smaller. Okay, so again, all I did was distribute x minus 1 into my first power series, my y prime. So let's simplify this a little bit because we can. Well, we have, okay, writing this, don't forget, I mean, I know this is tedious to write this over and over, but you have to write the summation notation, otherwise it's not a sum. We have n, cn, right, and this guy is a 1, so that's really x to the n, which we love because we want an x to the n. That's pretty much it for this. Let's just go ahead and rewrite this. ncn, x to the n minus 1, and then our last summand, Cn x to the n equals 0. Okay, so distributed, it's simplified. So now we look at our powers of x, right? So we have x to the n, okay, x to, and then we have 2 terms here, and then we have x to the n. So let's change this by using a dummy variable. So I'm going to let k be x to the n. So let k be, or n minus 1. Let k be n minus 1. Okay, so if k is n minus 1, then n must be, right, just solve for n, is k plus 1. So I'm going to go, again, I'm using the dummy variable notion here. Okay, so let's, again, rewrite your summand that you're not using. And okay, so let's change our these guys. So we have, okay, so summation, I'm going to wait to write my index. My n is, well, I called it, it's x plus 1, so or k plus 1. And cn, so let's just see k plus 1. X to the, and then this is all in k. And again, notice I started with n equals 1. So if n is 1, well, if n is 1, then I know k is 1 minus 1, which is just 0. So that's how I know to start with k equals 0. And that's pretty much it. I'm just writing this guy. Cn x to the n equals 0. Okay, so we have our x to a power, and x to a power, right? All these guys. And again, this is a dummy variable, which means it's just a placeholder. If you want to call k star, or let a happy face, or a heart, or a square. I mean, it's just a placeholder. Okay, so now the next the next part is to find our, let's make our indices the same. So we have n equals 1, so we have 1, 0, and 0. So I probably want to put, I want to make these all 0, because I know that, and we did this in a previous example, if I rewrite this command and I start at 0, am I changing anything? Is this the same thing as this? And it is the same. Again, because if n is 0, well, the first term here is 0, because 0 times anything is 0. And then n equals 1, n equals 2. Well, if you start with n equals 1 here, again, you have the same series. Here you're just adding a 0, which doesn't change the value of this command. So I'm going to replace that. And again, this is the second part is a dummy variable, so I'm going to replace my k with n's because I'm working with n's. So n 0 to infinity, n plus 1, c n plus 1, x to the n plus 2, and we have cn x to the n, and n equals 0 to infinity. Okay, so let me make this a little bit smaller. And again, I mean, if you have some, reservations about this guy being equal to this guy by just simply changing k to n, I encourage you and I challenge you to, to write this power series out, and you'll notice that you'll have the exact same terms in each power series. Okay, so indices are the same, so our happy campers. Our powers are the same, so we're happy campers. So now we're ready to use, we can use our power series operations that we learned in algebra. So let's see, we have our summation notation, and let's see, I'm basically factoring out x to the n. So I have n, cn minus n plus 1, cn plus 1 plus 2cn. Right, again, all I really did was factor out that x to the n. And all of that is equal to 0. And we want to use our identity principle. So this implies, and this is by identity principle in your book, principle, I can say n times cn minus the quantity n plus 1, that's a plus, cn plus 1 plus 2cn is equal to 0. Okay, so remember our goal, one of our goals is to find a recurrence relation. So we can definitely solve for cn plus 1. And let's see, we can actually do something before, make this, to simplify this. I see a c to the n, and I see a c to the n, so I can write that as, okay, I don't like how I wrote that. That is n plus 2 c to the n's, and then I have this guy. Okay, so that looks a lot nicer. Next part. You can even, I'm going to add this guy to both sides. N plus 1, cn plus 1. Ooh, this is looking very nice. Let's solve for cn plus 1. Well, cn plus 1 is n plus 2 cn all over n plus 1. So this is our recurrence relation that we want to define. So recurrence relation. And I'll go ahead and stop here because it's getting close to 10 minutes. And again, I want to chunk this up. We'll explore this pattern in the next video and hopefully find a power series solution.